In this lesson, we're going to be solving systems of linear equations. Both of the equations that we'll be working with in our problem will be linear equations. That is, when graph produce straight lines. To get us started, we have to look at some terminology. We want to look at the term consistent and inconsistent. A system of linear equations is either a consistent system or an inconsistent system. If a system of linear equations is inconsistent, then we would just name it inconsistent and move on. However, if a system of linear equations is what we call a consistent system, then that consistent system can be qualified as either independent or dependent system. So we're going to put two more words down here: independent and dependent. So to help us understand these four terms, we're going to draw three systems on three coordinate planes. So let's go ahead and draw three coordinate grids here. Now, when we take two lines, there are several things that can happen when you put two lines on one particular coordinate plane. It can be that when we draw a line and then we draw another line, this is a system of linear equations because I have two or more lines graphed. It's possible that those two lines intersect in only one point. What if we took two lines, but they never intersected, therefore they're parallel with no intersection points? Or the third and final case of what we can do with two lines on a coordinate plane is that when we graph one, but then we go to graph the second one, it actually is the same or equivalent to the first line where they lay on top of each other. So here we have one point of intersection. Here we have no points of intersection. Yet here on this system, we have all points that are on one line are also going to be on the other line. So let's go back to our terms up here. So a system is either consistent or inconsistent. Well, let's start with this system right here. There are no points of intersection, so think about that word inconsistent. That word is connected to no points of intersection. This system is said to be inconsistent. They have no points of intersection, they're parallel. So we don't say anything else about this. We don't say that this inconsistent system is independent or dependent. We just walk away from this language. All right, let's look at the other two remaining situations here. Both of these remaining situations are represent consistent systems. That means they have at least one point of intersection or more. So this is a consistent system. It has an intersection point, and this is a consistent system because it has many points of intersection. Once we label a system as consistent, then we have to further qualify, is this system independent or dependent? We would call this consistent system here independent because these two lines are independent of one another. They have only one point of intersection. Now looking at this consistent system, we see that we have the same line, so we call this a dependent consistent system. So as we go through and solve systems of linear equations by using a new method, we're going to go ahead and describe further what type of system we have. All right, so in this lesson, we're also going to be looking at a new method for solving a system of linear equations. We're going to solve by the elimination method. We have 5 examples. So in example 1, we're going to have x plus y equals 0, and we're going to have 3x plus 2y equals 1. Both of these equations, when graphed, will produce a line. So according to these three situations that we have right here, okay, what best represents what's going on with these two lines right here? All right, using the elimination method, what we're going to do is we're going to try to decide, do we want to eliminate the x terms or the y terms? And we look at it kind of vertically. We kind of look at it like, okay, I've got x and 3x, but I want to eliminate, the x's here. So if I chose to eliminate the x terms, it would be best if I could have a -3 in front of this x variable here, so that when I add down, those two terms are eliminated. We can also choose to eliminate the y's if we want to. Sometimes it's easier to eliminate one of the variables over the other, just depending upon the kind of work that you have to do. All right, the elimination method has us decide which which term we want to eliminate. So I think I'll just go with saying, let's just go ahead and eliminate the x terms. So we kind of ignore everything else and I go, okay, well, what can I do to put a -3 in front of x here? Well, I can take that top equation and I'm going to kind of wrap it up here in some little parentheses. And I'm going to say, you know what? I'm going to multiply every term in that top equation by -3. But I'm not going to change the bottom equation. I'm just going to rewrite it again here. Now I'm going to kind of draw this little squiggle mark because I'm not ready to add down. When I want to add down, I'll draw a straight line to indicate that I'm summing. So now what do I do? Now I need to multiply -3 into all terms that are in the top equation. So I'm going to just re-record it down here. So -3x minus 3y equals, don't forget to multiply -3 by 0, you still get 0. Now I'm just going to re-record the bottom equation that I'm not going to make any adjustments to. Now I'm going to draw a straight line as opposed to a squiggle. There's no mathematical reason for that. That just tells me I'm not done yet. Now let's look at these two equations in a vertical format. When I add these two terms, they actually cancel. I'm left with 0. Now let's add down the y terms. Well, -3y plus 2y makes -y equals, let's add the constants, that's 1. Of course, let's solve for y now. So divide both sides by -1. So positive y is equal to -1. To continue solving, now we have to get the x value. So you can go back to any of the equations that we worked with. I think I'll just go back to the top equation here. And now I need to solve for x. So using the top equation, I have x plus, now y was -1, so that could have just made that x minus 1, but I'll just do a -1 here, equals 0. Now let's take and add 1 to the other side. These will cancel, x equals 1. So putting these values together in the correct ordered pair format, x first, y second, what happened is that I just got one point of intersection. This is the only ordered pair that satisfies this system. So that's my solution. Because I do have a solution, we're going to call this a consistent, independent, because there's only one point of intersection, independent system. Consistent and then independent. Let's see if I can squeeze another example here. Number 2. So x minus y equals 2 and -2x plus 2y equals 5. If I'm using the elimination method, I'm going to eyeball the x terms. I see that if I multiplied this top equation by +2, that I could add down and my x terms would cancel. So that's going to be my approach. I'm going to multiply the top equation. I'll kind of wrap it up in parentheses here by -2. I like to show the arrows, that way I won't forget to multiply -2 into all the terms. I'm going to re-record without any changes the bottom equation in the original problem. Kind of do a little squiggle because I'm not ready to add down yet. I've got a multiplication I need to do. So -2x, -2 times -y is +2y, and then 2 times -2 is -4. Re-record. Why did I multiply by -2? I needed to multiply by +2. Oh, I don't want to restart the video. All right, let me come back up here. Let me multiply by +2. So this would be positive 2x. This would still be negative 2y. And this would be positive 4. So 2x minus 2y equals 4. Correct. Re-record the bottom equation. Negative 2x plus 2y equals 5. Straight line means now we're ready to look vertically and add down. Those will cancel. And look what happens here. The y's also cancel. So what we end up with is 0 to the left of the equal sign. And we end up with the expression 0 equals 9. Well, what does that tell us and what does that inform us mathematically? Well, we know 0 does not equal 9. So when we get a situation like this that's false, we want to think back to our 3 pictures here. We don't have a consistent system because we don't have an answer. So it must be that these 2 equations represent lines that are parallel. So our answer is inconsistent. So when we get a false statement, no intersection point, we want to think about 2 lines that are parallel that would never give us an intersection point. Okay, we'll go to example 3. Right, we want to solve this system of linear equations. So I'm just going to take a look at the x terms first. If I multiply the top equation by positive 2, I would get positive 6, and that would cancel with the negative 6x. So that's what I'll do here. And bring down the top equation. Wrap it up in parentheses, show I'm going to multiply by positive 2. Maybe draw your arrows so you don't forget to multiply 2 by every term. Re-record the bottom equation. Don't make any changes to it. I'm going to draw a little squiggle because I still have the multiplication to do. So I'm going to end up with 6x minus 4y equals 10. Re-record the bottom equation. Straight line. Now let's look at it vertically. The x terms will cancel. Oh, the y terms will cancel again. So again, we record 0 to the left of the equal sign. But here, notice that those 2 numbers also collect to 0. Now this is different than the previous example because this is a true statement. This is 0 equals 0. So when we get this situation and this is true like this, then we look back at our 3 examples here. Okay, this tells us that our system is consistent, so it's one of the ones here or here. And because we're not getting one intersection point, it must be that we're going to have this consistent dependent situation where we actually have the same line. And we can go back and look at the equations and go, oh, yeah, these are the same lines, because if I took this bottom equation and I changed all the signs in it, I would get back to what the top equation is exactly. So this is a consistent dependent system. Same line. So for example 4, I thought I'd throw in some decimals. Let's make sure we know how to handle the decimals. For me personally, I'm kind of inspecting this top equation. And if I multiplied everything by 10 in the top equation, that would move the decimal 1 place to the right on all these terms. So then I would eliminate the need to work with decimals. Or you might want to just think about, let me just move the decimal 1 place to the right. Well, that's the same thing as multiplying by 10. So I'm going to take the top equation and first of all, just tackle the decimal issue. And then I'll tackle in the next step which term I'm going to cancel. Wrap this top equation up. Just say you're going to multiply by 10. Draw your arrows. Re-record the bottom equation. Little squiggle line. 18x plus 12y equals 40. Re-record the bottom equation. Now I see that if I multiply the bottom equation by -2, that 9 would turn into a -18, and that would allow me to eliminate the x terms. Seems like I'm picking on eliminating the x terms in all these examples, but it's just the first one I happen to look at. But if I don't feel like it'd be an easy elimination, then I might look at the y terms to see if that is an easier elimination. Okay, now right here, what I think I'm going to do is just kind of wrap this up in parentheses and show myself that I'm going to multiply by -2. Little squiggle line. Now I'm going to re-record the top equation. Multiply in the -2 to all terms. -12y and -6. The x terms cancel, that's 0. Oh, the y terms cancel also. So now we end up with 0 equals +34. Well, again, 0 doesn't equal 34, so what does that inform us? This is going to be an inconsistent system. I have no points of intersection. I don't have any answers. So I have two parallel lines. All right, and example 5. Thought I'd throw in an example that has fractions in it because we could always use some extra practice with fractions. All right, kind of like the last example in example 4, I want to tackle getting rid of the fractions first. I don't even want to concentrate on eliminating one of the terms yet. Let me just work with nice numbers, especially if I don't have a calculator. So if I want to eliminate in the top equation these fractions right here, what we do is we look at the denominators of all the fractions in the top equation. So 5 and 2. 5 and 2 both divide into 10. So 10 is what we call the least common multiple. So I'm going to actually take and multiply the top equation, which I'm re-recording right here. Okay, I'm going to multiply this top equation by 10. So kind of wrap it up in parentheses, show that we're going to multiply by 10. Again, we're not solving yet. We want to get rid of all these fractions. Now let's take a look and inspect the bottom equation, okay, which also has fractions. And I notice that 10 and 4 both divide into 20. 20 is the least common multiple. So I'm actually going to take the bottom equation and multiply every term by 20. So re-record and show that we're going to multiply by 20. Little squiggle here. All right, let's go back to the top equation. Now 2/5 times 10. Let's tackle that first. What is 2/5 times 10, which we can put 10 over 1 if that's helpful. Well, you might multiply the tops together and the bottoms together. That's fine. I always look for something that's going to make my work a little bit easier. I see that 5 is a common factor of 5 and 10. 5 divides out of 5 once, and 5 divides out of 10 twice. That leaves me to multiply the two 2's on top, so I get 4 over 1. I don't need the 1 in the bottom, so I just have 4 when I multiply here. So the purpose of multiplying 10 by 2 over 5 is to get rid of the fractions. And so I do. I get 4, and I still have the x. Now it's time to multiply 10 into the -3/2. So -3/2 times 10 over 1. You can get -30 over 2. That'll give you -15. But I see a common factor of 2 to take out of both 2 and 10. That leaves me to multiply -3 by 5, and I get -15. I get the 1's in the bottom, so I get -15y, and then don't forget to multiply the 10 into the 4, 40. All right, same process with this bottom equation here. 1/10 times 20 would be 20 over 10, or just simply 2x. -3/4 times 20 over 1. Again, you can get -60 over 4. But I see that 4 is a common factor of 4 and 20. So 4 divides out of 4 once and 4 divides out of 25 times. So I get minus 15y equals, and then I multiply the 20 into the negative 2 and I get negative 40. Now that I've tackled getting rid of the fractions, now I'm going to take a new look at this and go, okay, what do I want to eliminate? Do I want to eliminate the x's or the y's? So for me, I think eliminating the y's would be the easiest. I just need to multiply either the top or the bottom equation by negative 1. So at this point, I'm going to show, I think right here, I'm going to wrap this up and say, you know what? Now it's time to multiply the top equation by negative 1. So I still have my squiggle. Let's distribute that negative 1 in, changing all signs in the top equation. Re-record the bottom. Just be careful. Always go back and double check that you re-recorded correctly because you can make a mistake, just as easy as I did in that previous example. I'm now ready to add down. So here I'm going to get negative 2x, the y terms cancel, equals, and this collects to negative 80. Divide both sides by negative 2. X equals positive 40. Okay, so now we got to solve for y. I am not going to go back to one of the original equations because they have fractions in it. I'll probably go back to one of these two equations here. I guess I'll just pick on the top equation. So I'm going to pick on 4x, but I know x is 40. So 4 times 40 minus, let's see, I picked this one, right? Minus 15y equals 40. So 4 times 40 is 160. I'll subtract a 160 from both sides. Don't forget to bring down your negative. Collect here, that's negative 120. And then as a final step, let's divide by negative 15. So it looks like y is going to be, I want to say that's 8. So we could see from way back here when we got a value for x that we were going to have a consistent independent system. So our solution is 40, 8. Because we have a solution, this is a consistent system. And because we have only one solution, okay, this is independent. The two lines are not the same lines. Alrighty, so that was it. That's solving by elimination, but then also further qualifying what our solution is, whether it's consistent, inconsistent, if it is a consistent system, if it's dependent, or if it's independent.